Imagine an animal lost to the mists of time, vanishing some 13 millennia ago, the formidable dire wolf. Now, this creature of ancient legend is said to walk among us once more. Brought back through the cutting edge of genetic engineering. At least, according to the claims of Colossal Biosciences. This ambitious company further asserts that the future holds the potential to resurrect numerous other iconic extinct species. Consider the Tasmanian tiger, a unique predator that once roamed the Australian landscape. The dodo bird, a flightless curiosity that disappeared from Mauritius in the 17th century. Or the colossal woolly mammoth, an Ice Age giant related to modern elephants that inhabited frigid northern territories until its extinction roughly 4,000 years ago. Colossal Biosciences heralds the dire wolf as their inaugural triumph in the field of de-extinction. This captivating canid, a distinct species of wolf, gained widespread recognition through its portrayal in the Game of Thrones television series. In the show, many key characters were accompanied by these imposing companions. Inspired by this cultural phenomenon, the initial pair of dire wolf cubs brought into existence through the company's efforts have been christened Romulus and Remus. Their names echo the mythical founders of Rome. This groundbreaking project unfolded at a clandestine facility within the United States. Here, captured on video, we witness these young specimens basking in the warmth and frolicking within the confines of a barn. At a mere 5 months old, these remarkable creatures remain oblivious to their extraordinary circumstances. They've been born into a world where no other members of their lineage currently exist. Joining them is a third dire wolf, a female. The company has bestowed upon her the name Khaleesi, another nod to the fictional world that fueled public fascination with these animals. The initial reports evoke a sense of wonder and possibility. However, this ambitious endeavor has not been without its share of scrutiny. Numerous voices have emerged, challenging the veracity of the company's claims. Many experts contend that what has been achieved is not a true resurrection of the ancient dire wolf. Instead, they argue it's a genetically engineered variant of a contemporary wolf species. The central question remains, how is this feat accomplished? In this video, we delve into the science and the debate surrounding this fascinating and potentially controversial undertaking. Fast forward to 1854. On American soil, near the banks of the Ohio River, paleontologists unearthed the very first fossil evidence of the creature we now know as the dire wolf. Just 4 years later, in 1858, the distinguished American scientist Joseph Leidy proposed that this formidable animal belonged to the Canis genus, the same classification as modern dogs, wolves, and coyotes. It was from this initial assessment that the dire wolf received its scientific designation, Canis dirus, aptly translating to fearsome dog. Indeed, all canid species from our domesticated companions to wild wolves and the elusive coyote fall under this Canis umbrella. However, in 1918, a contrasting perspective emerged from the work of scientist John Merriam. While meticulously examining dire wolf fossils recovered from the La Brea tar pits in Los Angeles, Merriam observed significant anatomical distinctions. He argued that these differences were so profound that the dire wolf warranted its own distinct genus, separate from Canis. At the time, Merriam's assertion was met with skepticism and largely disregarded. Consequently, for the ensuing century, the prevailing scientific understanding held that dire wolves were close relatives of gray wolves and other extant Canis species. But in 2021, a groundbreaking study published in the prestigious journal Nature irrevocably altered our comprehension of the dire wolf's evolutionary history. Through meticulous analysis of fossil remains, researchers conclusively demonstrated that dire wolves were not merely a larger version of modern wolves. Their evolutionary trajectory diverged from other Canis species approximately 5.7 million years ago. This pivotal research also revealed that dire wolves coexisted in North America with gray wolves and coyotes for an extensive period. Yet, remarkably, there was no evidence of interbreeding between these distinct lineages. Their genetic pools remained separate. Then, around 13,000 years ago, the dire wolf vanished entirely from the face of the earth. While gray wolves persisted, the precise reasons for this extinction remain a subject of ongoing scientific inquiry. One prominent hypothesis suggests that dire wolves, being adapted to hunt larger megafauna, succumbed to extinction as their primary prey species disappeared during the late Pleistocene extinction event. Another theory posits that their inability to interbreed and adapt as readily as gray wolves left them vulnerable to environmental shifts. When juxtaposed with modern gray wolves, dire wolves were a substantial 25% larger on average. The Game of Thrones depiction, portraying them as lion-sized behemoths, takes a degree of artistic license. However, it is accurate that their skulls were proportionally longer and broader than those of other wolves, and their jaws possessed a significantly more powerful bite. Their coat is believed to have been a lighter, almost white hue. And like their modern relatives, they likely lived in social packs, facilitating cooperative hunting of larger prey. This brings us to the central question. How did Colossal Biosciences purportedly achieve the de-extinction of a dire wolf? De-extinction, in its essence, is the reversal of extinction, the endeavor to bring a species back from oblivion. Broadly speaking, there are three primary methodologies under exploration. The first of these is backbreeding. This technique involves selectively breeding living relatives of an extinct species that exhibit traits reminiscent of the lost form. Over successive generations, the aim is to amplify these ancestral characteristics, gradually recreating an animal that physically resembles the extinct species. A compelling case study in backbreeding is the quagga project. Observe this fascinating creature, the quagga. From the front, it bore the distinctive stripes of a zebra, yet these markings faded along its flanks, giving way to the more uniform coloration of a horse on its hindquarters. This unique equid once roamed the plains of South Africa, but was tragically driven to extinction by relentless hunting, with the last known individual dying in 1883. In 1987, a dedicated group of scientists initiated the quagga project, an ambitious attempt to bring this animal back through backbreeding. Their approach involved identifying plain zebras exhibiting reduced striping, particularly on their rear limbs. These zebras were then selectively bred, with each subsequent generation prioritizing individuals displaying fewer stripes. As you can see in these images, spanning from the initial zebra with slightly reduced stripes in 1987 to animals born as recently as 2022, the resemblance to the extinct quagga is striking. The Quagga Project's website offers further insights into their ongoing efforts. This meticulous process is the essence of backbreeding. However, a fundamental question arises. Does achieving a visual likeness truly equate to bringing back the quagga? There are undoubtedly subtle genetic and potentially behavioral traits of the original quagga that remain unknown to us. This is a significant limitation of backbreeding. While we may create an animal that bears a superficial resemblance to an extinct species, its genetic makeup will inevitably differ. The second de-extinction technique is cloning. This method offers the theoretical possibility of creating a precise genetic replica of an extinct animal. However, a crucial prerequisite for cloning is the availability of intact and viable cells from the extinct species. The process involves extracting the nucleus containing the genetic material from a cell of the extinct animal and inserting it into the enucleated egg cell of a closely related living species. While conceptually straightforward, the practical execution of cloning is exceptionally challenging. It wasn't until 1996 that the first mammal, Dolly the sheep, was successfully cloned, a landmark event widely covered in educational curricula.
Dolly, who made her debut for the press today, is a remarkable sheep. She's the first sheep to be cloned from another adult sheep. Clearly enjoying the attention, scientists say she's developing normally.
The first attempt to utilize cloning for de-extinction occurred in 2000 with the Pyrenean ibex, or bucardo, a subspecies of Spanish wild goat that was critically endangered. Tragically, the last known bucardo perished on January 6, 2000, marking its extinction. Fortunately, in the year preceding its demise, scientists had collected and cryogenically preserved tissue samples containing its cells. This provided the opportunity for a cloning attempt. Researchers transferred the nuclei from these bucardo cells into the enucleated eggs of 57 domestic goats. The success rate was dishearteningly low. Only 7 goats became pregnant, and 6 of these pregnancies resulted in miscarriage. Ultimately, only 1 goat gave birth to a female bucardo kid. However, this newborn suffered from a severe lung defect and tragically died within 10 minutes of birth. This poignant case illustrates the immense difficulties inherent in cloning, leading some to quip that the bucardo became an animal that went extinct twice. This brings us to the third and most relevant to our dire wolf discussion method of de-extinction: genetic engineering. Now, let's delve into what is considered the most cutting-edge and potentially transformative approach to de-extinction: the fossil DNA method. This technique hinges on the remarkable fact that the genetic blueprint of long-deceased creatures can persist within fossils for millennia, a testament to nature's own data preservation system. To truly grasp this third pathway to bringing back the extinct, consider the following. Scientists embark on this process by meticulously extracting DNA fragments from the fossilized remains of extinct animals. These precious molecular relics are then subjected to intense scrutiny. The goal? To precisely identify the genes that define the lost species. Subsequently, these ancient genes are laid alongside those of the extinct animal's closest living relatives for detailed comparison. Following this genetic juxtaposition, the power of modern DNA editing comes into play. Scientists strategically alter specific genes within the cells of the living relative, essentially recoding them to mirror the genetic instructions of the extinct species. Once these cellular transformations are complete, the subsequent stages echo the familiar process of cloning. The modified cells are introduced into a host animal, and if all goes according to plan, the resulting offspring will possess the newly engineered genetic heritage. However, this ambitious endeavor is fraught with formidable challenges. The primary obstacle lies in obtaining intact and comprehensive DNA from an animal that vanished perhaps thousands of years ago. Fossils, by their very nature, are often fragmented and degraded after their long entombment, and the delicate DNA within may be severely damaged or incomplete. Furthermore, the sheer complexity of genetic editing presents a second major hurdle. Manipulating millions upon millions of DNA base pairs with absolute precision is an undertaking of immense intricacy. In 2021, a visionary American entrepreneur, Ben Lamb, joined forces with the globally renowned geneticist George Church to establish Colossal Biosciences. This ambitious company was forged with a singular, audacious objective: de-extinction. And their flagship project, the one that captured the world's imagination, is the endeavor to resurrect the majestic woolly mammoth, a creature that last roamed the earth some 4,000 years ago.
Waiting for the right moment.
Their motto, "Waiting for the right moment," hints at the scientific rigor and patience required for such an undertaking, a sentiment I touched upon at the video's outset. Beyond the mammoth, their aspirations extend to the revival of the unique Tasmanian tiger and the enigmatic dodo bird. Yet, each of these iconic species presents its own unique and seemingly insurmountable set of challenges. The closest living relative to the woolly mammoth is the Asian elephant, an animal with a remarkable 22-month gestation period, the longest of any land mammal. The Tasmanian tiger, with its distinct marsupial biology like kangaroo, scurried its young in a pouch. Bringing a Tasmanian tiger to term would necessitate the creation of an artificial womb, a significant leap in bioengineering. And the dodo bird, being an egg-laying species, presents a different kind of hurdle, as manipulating genes within an egg poses considerable technical difficulties. In 2023, Colossal Biosciences convened a pivotal meeting, bringing together leading minds to deliberate on which extinct animal would serve as the optimal proving ground for their de-extinction technologies. It was during these discussions that the dire wolf emerged as a compelling candidate. Unlike more conventional research, animals such as sheep, goats, and rats, dire wolves hold a prominent and captivating place in popular culture. Beyond their dramatic portrayal in Game of Thrones, they feature in the immersive worlds of World of Warcraft and the imaginative landscapes of Dungeons & Dragons. This pre-existing cultural fascination likely played a significant role in their selection, with the understanding that a successful dire wolf revival would garner substantial public attention and support. Thus, in the summer of 2023, the dedicated team at Colossal Biosciences embarked on their ambitious dire wolf project. Their initial and critical challenge was to locate high-quality, well-preserved dire wolf DNA. Two particularly promising fossil specimens were identified. The first, a 13,000-year-old tooth fragment, was unearthed from the depths of Sheridan Cave in Ohio. The second, a 70,000-year-old skull, was discovered at the American Falls Reservoir in Idaho. Utilizing these ancient relics, the scientists initiated the intricate process of gene sequencing. The data gleaned from these two samples proved to be remarkably rich, reportedly exceeding existing dire wolf genetic information by a factor of 500. However, it's crucial to understand that this did not represent the complete genetic code of the dire wolf. Rather, it provided valuable, albeit fragmented, insights. The precise percentage of the dire wolf genome successfully recovered from these fossils has not been publicly disclosed. The subsequent crucial step involved a detailed comparative analysis, pitting the recovered dire wolf DNA against the genetic code of its closest living relative, the gray wolf. According to Colossal Biosciences, the gray wolf shares an impressive 99.5% genetic similarity with the long-extinct dire wolf. This close kinship significantly streamlines the de-extinction process. By studying the function of specific genes in the well-understood biology of the gray wolf, scientists can formulate informed predictions about how corresponding genes might have functioned in the dire wolf. The third pivotal stage involved the strategic selection of which genes within the gray wolf's DNA would need to be altered to nudge it towards the characteristics of a dire wolf. The company ultimately focused on modifying 14 specific genes, primarily those governing external, observable traits. These included key features such as the overall size of the animal, the dimensions of its head, the coloration of its fur, and the density and texture of its coat. With these target genes identified, the fourth step involved the precise application of gene editing technologies to enact these changes within the gray wolf's genetic material. The powerful tool employed in this endeavor was CRISPR-Cas9, a revolutionary technology often likened to genetic scissors for its ability to precisely cut and modify DNA sequences. The intricate workings of CRISPR-Cas9 are a fascinating subject in their own right, perhaps deserving of its own dedicated exploration. For their groundbreaking development of this transformative technology, French scientist Emmanuel Charpentier and American scientist Jennifer Doudna were jointly awarded the Nobel Prize in Chemistry in 2020. Leveraging this powerful gene editing technology, the company meticulously executed approximately 20 specific alterations across those 14 carefully selected genes within the gray wolf cells. These modified cells were then propagated in vast numbers within a controlled laboratory environment. The project advanced to its next critical phase in mid-2024. Scientists carefully extracted the nucleotide genetic command centers from these engineered cells. In parallel, they obtained unfertilized egg cells from domestic dogs and skillfully removed their own nuclei, creating empty cellular vessels. The engineered gray wolf nuclei were then delicately inserted into these enucleated dog egg cells, a process akin to a high-tech genetic transplant. A total of 45 such reconstructed embryos were then implanted into 2 canine surrogate mothers, marking a significant gamble. Ultimately, only 2 of these pregnancies progressed to term, highlighting the inherent challenges of interspecies gestation. Finally, on the 1st of October, 2024, the culmination of this intricate process arrived with the birth of 2 pups via cesarean section. The initial plan had been to allow for natural delivery, but concerns mounted regarding the potential size disparity between the genetically modified cubs and typical dog puppies, which could have jeopardized the health of the surrogate mothers. Thus, on that momentous day, the 2 dire wolves were born and christened Romulus and Remus, a symbolic nod to the mythical founders of Rome. In their fragile early days, the dire wolf pups relied on the milk of their canine surrogate mothers for nourishment. However, this maternal milk proved insufficient to meet their rapidly growing metabolic demands, necessitating supplemental bottle feeding soon thereafter. Technically speaking, these 2 cubs are near-perfect genetic clones of each other, carrying virtually identical DNA within their cells. Yet, a fascinating observation emerged. Despite their shared genetic blueprint, Romulus and Remus exhibited distinct temperaments from their very first days. Remus displayed a notably bolder and more exploratory nature, while Romulus presented as somewhat more reserved and shy. This divergence underscores a common misconception surrounding cloning. While the term often conjures images of identical beings in both appearance and behavior, the reality is far more nuanced. Even with identical DNA, an individual's behavior and personality are shaped by a complex interplay of factors, most significantly the environment in which they develop. Furthermore, even identical genes can manifest in subtly different ways, influencing the expression of various traits. Predicting the precise activation and silencing of genes remains an exceptionally complex biological puzzle. This principle holds true even for animals brought back from extinction. An animal's fundamental being is not solely dictated by its DNA. It is also profoundly influenced by its mother and other caregivers. The surrounding environment, the quality of its diet, and even the intricate community of microbes that reside within its body. Countless factors converge to shape a unique living organism. But let's return to the unfolding narrative. On the 30th of January, 2025, a third dire wolf, a female named Kaliesi, joined the small group. Ben Lamb, a driving force behind Colossal Biosciences, has stated that these 3 individuals will not be permitted to breed. The company's current plans involve facilitating the birth of only a limited number, perhaps 3 to 5 more such genetically engineered animals. These dire wolves will be housed within secure, private preserves, protected by 10-foot-high security fencing and sophisticated drone surveillance, with access granted only to a select few, reportedly including wealthy investors. Now, I urge you to momentarily consider this endeavor from the perspective of these unique creatures. They are at an age when, under natural circumstances, their parents would be imparting crucial survival skills, such as hunting. Yet, they are orphans, never having known their biological parents, or even encountered another member of their kind. Their entire existence will unfold within the confines of a highly artificial and controlled environment, a far cry from the wild existence of their extinct ancestors. It is a sobering thought that, perhaps a decade or two hence, upon their eventual passing, these animals could face a fate similar to the Pyrenean ibex, the bucardo, becoming the second species in history to go extinct, twice. From a purely scientific standpoint, this achievement undoubtedly represents a significant technological milestone. However, the considerable criticism it has drawn is also entirely warranted. The true essence of de-extinction should not merely be the creation of a living spectacle, a novelty for photographs and fleeting entertainment. Its ultimate aim should be the successful re-establishment of a species within Earth's intricate web of life, allowing it to once again fulfill its ecological role. Much like the woolly mammoth, which played a vital part in maintaining the ancient Siberian grasslands. Back then, they were integral threads in that ecosystem's fabric. The critical question we must confront is this: if an animal like the dire wolf is brought back into existence, does it truly have a place within our contemporary ecological balance? Proponents argue that as a large apex predator, its reintroduction could help redress the current imbalance in certain ecosystems, particularly in regions like North America where it once roamed. They suggest it could help regulate prey populations and restore ecological harmony. However, when a private company invests millions in such an endeavor, one must ask, is the primary motivation ecological restoration? Or are there other, perhaps more self-serving, interests at play? The more likely scenario appears to be the creation of high-value, exotic exhibits within private reserves, or perhaps even zoological parks, serving primarily as sources of fascination and entertainment for a select few. Furthermore, there's the significant concern that the dire wolf's extinction some 10,000 years ago was a natural process, not driven by significant human intervention. Shifts in climate and natural changes within the ecosystem likely contributed to its demise. This raises a fundamental question: is there truly an ecological niche for the dire wolf in today's world? The very animals that once served as its primary prey may themselves be long gone. Reintroducing the dire wolf into modern ecosystems could lead to unforeseen consequences, potentially putting pressure on existing prey species hunted by gray wolves and other extant predators. Perhaps even setting the stage for a repeat of the ecological pressures that contributed to the dire wolf's initial extinction. Of course, all of this discussion hinges on a fundamental assumption that these creatures are, in fact, true dire wolves. But are they? The scientific consensus leans towards a more nuanced understanding. They are, in essence, genetically engineered versions of the gray wolves with a specific set of 14 altered genes. But consider the vastness of a genome, encompassing millions of genes. A mere 14 alterations represent a minuscule fraction, less than 0.001% of the total genetic code. While gray wolves and dire wolves shared approximately 99.5% of their DNA, these new dire wolves will also share only around 99.5% of their genetic makeup with their extinct ancestors. The simple biological truth is that to truly resurrect an extinct animal in its entirety, we would need a complete and accurate map of its entire genome, and the ability to make potentially thousands of precise genetic alterations. Consider this analogy. chimpanzees and humans share approximately 98.8% of their DNA. If scientists were to make 14 genetic changes in a chimpanzee to make it superficially resemble a human, would that truly make it human? The answer is unequivocally no. Perhaps our technological prowess and financial resources would be better directed towards the myriad species that are alive today, but teetering on the brink of extinction. Our focus should arguably be on safeguarding those creatures that already have a place within our planet's delicate ecological balance. Take, for instance, the northern white rhino. In 1970, over 500 of these magnificent animals roamed the African plains. Today, only 2 remain, both elderly. Upon their passing, this unique subspecies will vanish from the Earth forever. While scientists are actively exploring the use of advanced technologies to save the northern white rhino, the tragic reality is that we often lament the loss of biodiversity only when a species is beyond the point of no return. Countless other endangered species could still be saved through dedicated conservation efforts, often without the need for such expensive and ethically complex technologies. What is truly needed is a global commitment to protect our remaining natural habitats, free from the encroachment of unsustainable development and exploitation. While scientists diligently pursue innovative solutions, a broader societal shift in values and priorities is essential. A sobering 2019 United Nations report highlighted the staggering scale of the biodiversity crisis, stating that over 1 million species of plants and animals are currently on the precipice of mass extinction. If we dedicate our efforts to saving these species today, the need for futuristic and perhaps ultimately futile extinction projects may never arise. As the old adage wisely reminds us, an ounce of prevention is worth a pound of cure.